In previous class, we have studied about basics of PPA, right? Parallel prefix adder. So, and we talked about it's like different types in it, like Kogan-Stone adder, Brunt-Kung adder, right? And Shankly-Lansky adder, right? So, today we are going to learn about like what these three adders and why we need these three advanced adders, right? Okay. So, so till now we have studied about like ripple carry adder, CLA, CSLA, CSKA, and CSA, right? All these adders try to reduce carry propagation delay. Like the major goal of these adders was to reduce the like carry propagation delay that was occurring inside the like adders, full adders, right? So, however, when we have width becomes 32-bit, 64-bit, or even 128 bits, what happens in that type? Like if you input like if you receive input as 32-bit input or 64-bit or even 128-bit, like it's need to calculate like it's need to propagate its carry for 64-bit like it's need to propagate its carry for around 64-bit, right? So and for 128-bit it's need to propagate its carry for around 128 times, right? Like this it was happening in a ripple carry adder. Like if you use normal type of adder, it was happening like this. Okay. What was the major setback here? The major setback was that there was too much propagation delay. Okay. So to solve these problems, like engineers developed these parallel prefix adders, PPA. Okay. Basically the idea is very simple. Instead of calculating carries one by one, okay, like what we are doing inside a ripple carry adder, like the carry was right, it is propagating from one adder to another adder and next and to next adder, like it was going on. Okay, so there the delay was more. Okay, to solve this problem, okay, like instead of calculating carries one by one, we calculate many carries simultaneously using a tree structure. Okay, so in previous class I said about like a PPA we form a tree structure, right? So what happens inside the tree structure, like there will be a root node and there will be some branch nodes, right? So in that branch nodes this carry was used to calculate parallelly, like uh, some grouping was being done. Okay, like I said in the like generate and propagate group was going to done, like right, like that we are going to do here. We are going to like group previous and next GPs into one GPs, like that we are going to keep on going like in a tree form, then we are going to reduce at last at one node, right? So this was like they were doing this parallelly, like this was like input level and stride one, like level one, level two, and at last level three. Okay, so this was the concept we have used inside this PPA, right? So because of this tree structure, delay reduced from O of n to big O of log to the base 2n. Okay, so this was happening inside the tree structure, right? So like before going to this coconut stone and other adders like landscape and branch force adder, so we should memorize about some the concept, some basic concepts. Okay, so just try to recall the concepts like generate and propagate signals. Like I said, generate, how you are going to calculate generate and propagate signal. Generate signal you can write with the equation called as gi is equal to ai and gate of bi. Okay, so whereas in a propagate signal like pi equals to ai XOR operation bi. Like what does the generate signal means? Generate signal means Like it works only in the case like if both the inputs, like input A, input B, are as like input as one, then only the generate signal is going to generate. Like it's saying that I'm generating a carry. Okay. So when does the propagate signal like achieves one? When either one of the input should be one. Okay. Only one input should be one at a time. Okay. So that was the like case. Your propagate is saying, yeah, now I have only one input as one. Then I am going to propagate this carry that I have been received from the another adder. I'm going to propagate that carry to the next adder. Like this was going on inside like a propagate. Okay, so this was the job of the propagate signal. So every two like every PPA begins by generating two signals. What are the two signals? Generate and propagate signals. Okay, and also like what is and you also need to recall the like prefix operation. What is meant by prefix option? Prefix operation. Okay, there is like a entire PPA means a parallel prefix adder is built using one mathematical operation. Okay, and that is called as prefix operation. We learned prefix operation right here. This is the prefix operation. What is prefix operation? It's nothing but combining generate and propagating pairs. Okay, use like combining, you are going to form like something called as tree structure. Okay, so like what I said, it will look like this. You need to combine and it will form like a group. Okay, so this is meant like this was the operation. Using this operation we have built like a parallel prefix adder. Okay, so what does this operation do? As I explained, this operation is going to combine two neighboring blocks. Okay, and produce a large group. Okay, like I said, it's going to combine the previous like G and P signals with the present G and P signals. Okay, and it will form the group of that G and P signals. Okay, like G and P group of that G and P neighbors. Okay, it will do like that. Like just think. Okay, now you have bit. Think you have 4 bits. Okay, 4-bit inputs. In that, bit 0 and bit 1. In that bit 0 and bit 1, both bit 0 and bit 1 will have something called as generate and propagate signal, right? Like for bit 1, there will be having an on full adder, and bit 0, there will be having one full adder, right? So based on that full adder inputs, like in full adder FA0, okay, in FA0, what are the inputs you are going to give? Input like A of 0, B of 0, right? So that are the inputs is going to give inside a full adder FA0. Okay, means the zeroth bit group. Okay, which is zeroth full adder means FA0. Okay, like that. For there will be also a first bit, right, and second bit and third bit. Like this, we are going to assign for a 4-bit input, right? Like that, you are going to combine that bit 0's GP and bit 1 GP to form something called as uh, group, like 1 is to 0. 1 is to 0 is nothing but bit 0 to bit 1. Okay, so this was the main mathematical operation. Okay, nothing but called as prefix operation. So, and you should know about concept called as black cell. What are you going to do inside the black cell? Like in black cell, we used to like define something called as, we are going to combine both neighbors GPs and form a, and we need to transfer that GPs into next level, right? So this was the case of black cell, whereas gray cell, what we are doing inside the gray cell is nothing but we are like combining that both GP's neighbors, okay? But here we are only producing like generate, okay? We are only transferring generate. Why? Because in some cases, like look here, as I explained in previous class, see here, now you have this, okay? Now you are at level 1, okay? So if you are going to use a black cell, means you are going to produce a generate and propagate, okay? Now you have here group of generate and propagate, okay? And also you also have a group of generate and propagate, okay? Now you are going to use what black cell means. Now here you have group of generate and propagate, but just think, okay, this is the last cell, right? It means last output. Why should you have propagate here? Why should you have propagate? Means why you need propagate? Because you're not going to propagate your output to any other bit, right? Why should like there is no other option to propagate, right? At this level, like level 3, there is no option to propagate, right? So even if you propagate, where will you propagate, right? Just think in that way. So here we can't use black cell. Instead of black cell, we should use gray cell. So what does that gray cell does? Gray cell is nothing but it's only create like generate a carry. It does not going to propagate a carry. Okay, so it's just create a generate, means it's going to generate and it will add to your output. Okay, so this is what going inside the gray cell and black cell. Now these are the like basic concept you should know before starting Coxton order. Okay, so Coxton is the fastest PPA. Okay, like inside this adder, the speed is the highest priority. So that's why engineer chooses like Coxton adder for highest speed. Okay, so when I explain you guys like carry save adder, that time I said we are going to use here uh, ripple carry adder, right? And I also mentioned this Coxton adder, right? So for like normal operation, we are going to use ripple carry adder, but it sometimes like if you want highest speed, then instead of a ripple carry adder, we are going to replace it with by this adder, right? So why? Because the use of Coxton adder is speed, right? Okay, so it achieves the highest speed. So they are used in CPUs, GPUs, high performance processors. Why? Because they are used inside, because in this every like CPUs, GPUs and processors, we need speed, right? To achieve speed, we are going to use this Coxton adder. Okay, so before thinking about this Coxton adder and this fan out and minimum depth, we should know about like architecture. Okay, like just think, for 8 you have an 8 bits input. Okay, yeah, just think you have 8-bit input. Okay, so inside this 8-bit input, how we are going to like form a tree structure, and like how we are going to do it? This is what you are going to do. Okay, like think this is the bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. Okay, so this and are all your bits. Okay, like you have 8-bit input and you have separated that bits into bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. 0. Okay. So what hour you are going to divide like levels in that? Okay, like if you are going to divide the into level, like assign all the bits into, like divide into some parts, and that should be your basic like first level. Even like you can call this as stride also. Okay, so if you keep on going like apply black cell means, so 0 to 2, you will get something like this. Okay, like for sorry, this is your level 1. Okay, so if you keep on, yeah, wait. Okay, look at here, what you have inside stride 1, you have separate bits, right? So how does this bit looks like what are you going to do to reduce like or reduce or to combine this bit level? Like you are going to use a prefix operation, right? So what are you going to inside prefix operation? You are going to combine the gps, right? Gps of that particular group. So what is the sorry, like there shouldn't be on one box here. Okay, so just consider it as 4 box. Here you have 8, like 8, right? So if you are going to combine these using a black cell, means you will get, if you have 8 bits, then you are going to get here as 4 bits. Okay, so like how it's going to add bit 0 and 1 to one box, and bit 2 to bit 3 to another box, 4 to 5 to another box, and 6 to 7 another box. Okay, just like it shouldn't be there. Okay, so yeah, like this is going to like connect. Okay, so after that you will get straight to means level 2. So what is happening inside the level 2? In level 2, it is nothing but like it's telling I have grouped of like using black cell, I have grouped the neighboring like generate and propagate groups. Okay, now I have reduced that style levels, and after that what happens here inside? Now it's saying that after that I can still reduce. How? By grouping these neighbors, right? You can also group these neighbors. Okay, so if you group these neighbors means you're going to get like what you are going to get, you're going to get 0 to 4th bit, and like that, and 1 to 5th bit, right? So you're going to get like that, like 4 bits here and 4 bits here, like this you're going to get, right? So now you have group of 4th bit and 5th bit. Now you are not going to achieve like black cell. You need to like gray cell, right? So if you have gray cell, then you can say that uh, here I am going to generate only generate. Okay, so I don't want propagate here. Why should I need propagate? Because I don't want to propagate that to another bit, right? So it's thinking like that, and it's go for, and this will be your like last stride. Okay, so it will think like this, and it will generate the output. Okay, so just notice the pattern. Like I have mentioned something like if the level is right. So look here, I have mentioned here level 1, level 2, level 3, right? But there is another one called stride, right? Why I have mentioned like stride 1, stride 2, and stride 4? Why? because in every level, like level is just nothing but it's saying that how many depths this this input can produce. Okay, so like 8-bit architecture can only produce 3 bits, right? So 3 levels, but stride is nothing but it's going to tell about what is the operation, like what is the operation is going inside that particular level, like how many bits are going to come inside that particular level. So that's why in level 1 we had only one bit, right? Like bit 0, bit 1, bit 2, bit 3, bit 4. So we have mentioned stride 1, but here we have combined that bit 0 and bit 1, so we have 2 bits, and here also 2 bits, so stride 2. Whereas in level 3 we have combined this 2 bit and this 2 bit, right? So that's why we have 4 bits here. That's why I mentioned like stride 4 means nothing but it's going to say like what is the operation that's going on and what is that size of that particular box. Okay, it's thinking like that and producing the answer. Okay, I hope everyone got my point. So inside a binary tree, like stride doubles every level. Okay, so just think, if you have like next, if you have a level 4, then what is will be the stride there? The stride will be around stride 8. Okay, so this is very important. Okay, this is very important point, just remember. Okay, like how that level and stride differs. Okay, so in previous class I said, right, like how you are going to define the logic depth or depth levels, right? So by using this formula log to the base 2, and using this formula you're going to define what will be the stages. Okay, and what will be the like depths, minimum depths. Okay, like 8-bit as I showed, these are the depths, right? After this you are going to get answer. Okay, so these are the depth, level 1 depth, level 2 and level 3. It has 3 depths. Whereas for if you want to 64-bit, like you have n, right? Replace this n with 64 and calculate this answer. After that you are going to get like what are the levels or stages it has. Okay, so just think, for 64-bit, what were you doing inside a ripple carry adder? Inside ripple carry adder, we need to wait for 64 times, right? Like it's need to calculate carry for 64 times. Whereas in this parallel prefix adder, like cost on adder, you want to wait for around 6 stages. Okay, 6 tree levels. Like it is difference, right? It makes some difference, right? It's like waiting for 64 uh, level like carries, waiting for 64 carries in a RCE, like it's take too much time. Whereas waiting for like 6 tree levels, it's like it is somewhat less time. Okay, so that's why Coxstone add like adder as the highest speed. Okay, so what are the advantages of this Coxstone adder? Advantages are like fastest PP, fast means it has highest speed, lowest delay, uniform fan out, excellent timing. Okay, so I will explain about this fan out also. Okay, so disadvantages. What are the disadvantages? Like you all guys knows that even everything will have some disadvantages. Like, so nothing comes from free. Means everything, like every adder, there should be one limitation, right? So what are the limitations? Like it has some area, like it consumes larger area. Okay, so it has too many cells and also huge wiring congestion. Why? Like because you are going to connect it parallelly, right? Like in a tree form, means if you're going to connect like that, then the connection will be like, will be unend. Why? Because you need to connect with like every a bit with like the another bits, and like you need to form like neighbor groups. Those are things comes into the picture. Okay, so there you like use lot of long wires, right? So you're going to connect like a bit 0 to like another one bit in the right, like that. If you form is the wiring process takes too much cost. Okay, so these are the things that was happening inside this Coxstone adder. Okay, so next adder is Brent Kung adder. Okay, so why we need this Brent Kung adder? So Brent Kung adder was developed to reduce the area problem of Coxstone adder. Okay, so inside Coxstone adder we have some limitation, right? Like it's to take too much area. So to reduce that, we have like produce this Brent Kung adder. But here also we have some limitation. What? Because to reduce that area, okay, to reduce that area, we need to sacrifice some speed. Okay, so there, like think just like a Coxstone adder as it's the fastest adder. Okay, so but it has like a it takes highest area, like it's cover most of the area to maintain the speed and the area also. This is somewhere like Bradkang adder is something like just it's losing its some speed and maintaining the area. Okay, it's saying that I will give up my some speed, not like I'm not going to give my all speed. It's just saying that I'm going to sacrifice my some part of speed. Okay, so just think you are going in a 100 kilometer per hour. Okay, so at that time what happens? Like your vehicle will takes consumes too much of petrol, right? So to maintain that, to like to maintain the mileage, you are going to reduce keep your vehicle at around 60 to 80, right? So what happens in that time? At that time, like your economy will be good and your vehicle will maintain maintain some speed also, and it consumes less petrol, right? So like this, Brent King also is going to reduce some part of speed, and also it's reduce some free up some area. Okay, free up some part of area. So inside this Brent Kung adder, it uses two phases. Okay, the first phase is called as reduced tree, and the second phase is called as broadcast tree. Okay, so what is this reduced tree and broadcast tree? Reduced tree is nothing but upsweep. Broadcast sweep is called as downsweep. What is this meant by? So reduced tree means upsweep is nothing but combine. Okay, so the name itself says that reduced tree. Reduced tree means just like a tree structure. Reduce means you're going to keep on reducing that inputs, right? Like in level one we have 8 bits, and in like we have straight 2 and straight 4, like that we are going inside a tree structure. Like that only, it's going to combine in a reduced tree. Whereas in broadcast tree means downsweep means distributing the carry, means the carry you generated in level 1 will distribute it to other components, like that it's going to work inside this Brunton adder. Okay, So this is what happening inside a Brandkang. Okay. So if you need to get some ideas about this Brandkang adder means, just think of climbing a mountain, okay, and coming down. This will be a best example, okay. Like what happens if you're climbing a mountain? You can see like what go after going up and up by climbing a mountain, you will get like what are the things the viewer going to get from that mountain, right? So what are you going to do at a time? Like you're going to get collect, like you're will do somewhat like you're going to collect a information, like what are the things you're going to get, and how does the mountains looks from up, right? So after coming down, what are the things you're going to do? You're going to distribute that information, right? Like what the view you got, and what it, like how it meant to feel to climb that mountain, like that. You're going to distribute information with some others, right? So that are the phase that are used inside this Brent Kung architecture, okay. So how you are going to look here? I have just ignore this diagram color, okay. So because it has generated like everywhere black, 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 okay. So just think this and are also black, okay. Just think you have 8 bit, okay. Just like that Coxstone ladder, you have 8 bit, okay. For 8 bit architecture, you have something like this, like you have segregated into 8 bits. And after that, what you are going to do, you're going to do is upsweep, nothing but reduce phase, okay. Now you are going to reduce that using black cell. What does your black cell do? Your black cell is going to like combine bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. This was going inside that Coxton order, right? So like this, it's going to reduce the, it's in the inside the reduce phase, okay. So these are the things it will go. And after that, level 1, level 2, and in level 3, this will decrease into stride 4, okay. So this, just think this 4 also like black, okay. And these two will combine into one black cell, and these two will combine into another black cell, okay. Now you are straight for input. After that, you are going to get some more output, and you need to go down sweep, okay. Down sweep means broadcast phase means is nothing but you are going to distribute your carries, right? So just think in Coxton radar, after getting like level 3, you're going to get output, right? So but here you're not going to get output, okay. You need to distribute the carry generated in each, like your carry generated, right? Your carry generated in each steps, right? So how does the carry generate? Like like I said, if you are using black cell, what is the thing you are going to do inside a black cell? There is one thing, means it's going to generate and carry and propagate a carry, right? The use of the black cell is nothing but it's going to generate a carry and propagate a carry, right? So those sweep is nothing but the carries that are being generated in each step, okay. It's going to get distributed like this. This phase, this carry is going to distribute it like this and keep on going, okay, until you get for 8 bit there should be a 8 bit carry, right? So like that, it's going to get the carry distributed, okay. I hope everyone got my point. So just think for a Brent Kung adder, it takes less area, but the power also is less, but speed is not the fastest. Means it has moderate speed. Okay. So next going to landscape adder. So I also want to take like tell one thing. Here your depth will be not as Coxstone adder. Why? Because you are going two phases, right? One up sweep and down sweep. Okay. So you can't determine the depth. Okay. So your depth will be like not as minimum depth as Coxstone adder. So your depth will somewhat be, depends upon your input. Okay. So whereas coming to landscape adder, the main thing of the landscape adder is that landscape also achieves minimum depth like Coxstone adder. Okay. So it has somewhat same technique like how you are going to calculate minimum depth, right? Using the formula log to the base 2 n, right? Using that formula, you're going to determine the depth, right? So like that, same like Coxeter radar, it has the same trinity for depth, whereas the disadvantages of the problem that is going to occur inside a landscape adder is that it's going to create a fan out explosion. Okay, so what is fan out? Before thinking about fan out explosion, what is fan out? We should know about that, right? So landscape adder, like it uses divide and conquer prefix architecture. Okay, so like Brunt adder, I like forgot to say this. It's going to have a area efficient parallel prefix adder. How we are going to achieve this area efficient parallel prefix adder? Like you're going to create into two phase. Using the two phase, like your depth will become more, but your area will be less. Okay, it creates somewhat less area. Just think like that. Okay, so whereas in divide and conquer prefix architecture is nothing but like, wait, I will show, like how does this divide and conquer architecture works. Okay, like just think you have 8-bit inputs. Okay, just imagine you have 8-bit inputs. How we are going to divide that 8-bit inputs? If you're going to divide into two parts, then you will think something like 0 to 3 one part and 4 to 7 as another part, right? Like 0 to third bit as one part and 7 to, sorry, 4 to 7 as another part, right? So that is the meaning of divide. So after dividing, you need to split again, right? So if you split this again means how you are going to split? You are going to split that 0 to 3 as two parts, right? Like 0, 0 and 1th bit, and second and third bit as one group, and fourth and fifth bit and sixth and seventh bit as another group. Okay, so after dividing like this, like dividing your 8-bit inputs into alls and that also into another alls, after this like dividing, after this dividing process is completed, then you need to combine the results, right, to get carry that has been generated during this division. So that is what's called as conquer. Like after dividing, you need to combine to conquer that, right? So This is what the process going inside this landscader. Nothing but like keep on dividing and keep on solving. Okay. After like dividing, just combine the answer and you will get the carry that you should get. Okay. So this is also the way, same as Cockstone adder, but there we are like same what we is going to do like level 1, level 2, level 3, and after that we are going to combine the carry, right? Like that same process is going inside this landscape adder. Okay. So and this is landscape adder is also fast. Okay, comparing to Cockstone adder, this is also is very fast. Okay. So the problem is like I said, Cockstone adder as area problem, whereas this landscape adder as problem as fan out. Okay. What is meant by fan out? Okay, like how this fan out works. So just think you are at a highest level. So wait, hmm, what is the highest level here? The highest level here is level 3, right? So in highest level there will be many outputs, right? Like you are going to combine this every inputs output, like gps of this output is combined here and this output is combined here and this output is combined here. Like you keep on going to combine, right? And at last you are going to get this, right? So what you are going to do, like inside a Kongstone adder and Brent adder, you are not combining this, right? So just transmitting the output. Whereas in this like landscape adder, then architecture itself defines that it's going to divide and conquer, right? Means it's first keep on dividing into levels, and after that it combines the every answers. So what happens means, just think you have no only one node here at like at highest level you only have one node. Okay. So it has two outputs, right? Like one will be the sum and one will be the carry, right? But what is this sum and carry comprises of? The sum and carry comprises of this inputs combination and this input combination, and that's output is comprised of this and this, and like that it's keep on going, right? So for one node there will be two outputs. That two output you are going to get using these four outputs, right? This will have two outputs, this will have two outputs, right? Like that, that four output is comprised of eight outputs. How? Because this has two outputs, and this has two outputs, and this has two outputs, this has two outputs. Like that it's going to work, right? So just think, that is what's called as fan out. Means if you're going to combine the carries of these entire levels, okay, if you're going to combine the carries of this entire level, it's going to form this fan out explosion. Okay, nothing but fan out explosion means like combining the carries that are like sum and carries that are generating by all the levels. If you're going to combine that, then it calls fan out. Fan out means combining all the levels answer. Okay, so if you're combining everything inside this means it's going to create a explosion. Okay, because it can't handle that much of pressure. Okay, like adding all of this. Okay, that is what's called as fan out explosion. Okay, just like for example, a teacher is teaching 100 students directly. Okay, so what happens, the teachers will becomes overloaded, right? Like he can't answer each and every person's answer, right? Like in the same class. So that is the same problem occur inside the landscader. Okay, so what are the disadvantages of this landscader? I fan out, and if I and practical frequency reduced means like if you are going to combine that every outputs of other levels, obviously if you are doing that means your fan out explosion will occur. So the that aim of your producing your answer will become less, right? So that is what's called as practical frequency reduce means the frequency of your answer, maybe generator or not, will get reduced. Okay, so that is the thing happening inside this. Okay, so that's, I hope everyone got the difference between these three adders. Okay, so that's it for this class, guys.